Hello friends, today we are going to discuss about the BSc elective course PHE 10, that is Electrical and Electronic Circuits. And in any electronic circuit, the first and foremost thing that one requires is a power supply so that one can make any instrument work. Now, whenever a power supply is needed, we need kind of a circuit which will be providing us the required voltages and currents that our instrument requires for its good functioning. As you know, from the mains supply, we get a 230 volts AC as our mains input. Now, if we need any other kind of voltage from that, then we need to have a circuit which will be giving us the necessary voltage level, and also it is able to provide required current that is necessary for our instrument. To do this, we use a module called power supply, which all of you know. Today we will be discussing mainly about how to obtain a DC supply. DC supply, you know, is a supply where we don't have any alterations or variations in the current, but a kind of steady state voltage which is given to the resistor or load that we are going to put in form of our instrument. How to get that will be the topic of our today's discussion. Power supply is something that you need in various forms. Sometimes you need a very high voltage which is more than 230 volts also. So you have to convert that supply that you get from mains 230 volt supply into a higher voltage. Or sometimes you need lower supply, like sometimes we require for our like transistor radios or to operate, we need something like 6 volt, or sometimes we need 3 volts. All those supply that we need, sometimes we get them out of a battery cell. But it is not always possible to use the battery cells because the current requirements of our circuits are sometimes so high that the normal batteries will get drained so easily that you will have to keep on changing them very often. So we try to use the continuously available energy source to us, that is the mains supply, and convert the voltage in order to get a voltage which is our requirement, like equivalent to, like say 2 battery cells is 3 volts or 4 battery cells is 6 volts, so on and so forth. As you know, in digital electronics, if you have ever come across, then typically we need 0 and 5 volts as the operating levels in our digital signal. So there we need a supply with some plus 5 volts. So various requirements are there which will be catered by our power supply module, and for that we are going to discuss how one can convert from the AC mains that we get at our home or at our laboratory into the required DC voltage of our choice. So if you see, I just listed a few applications of our DC power supply. Like I told you, the transistor radio or audio amplifiers in our Wi-Fi systems, or very day-to-day for our computers, laptops or cell phones, we have chargers. All those chargers are essentially converting the AC mains into the required DC voltage. Then in laboratory when you work, there also for performing certain experiments, we need highly stable DC voltages. So these are the main application areas of DC power supply that we come across in our day-to-day life. So how do we get it? To get the desired DC voltage from AC mains, following steps are involved. First is that we have to convert the mains voltage into a lower AC voltage. As I told you, we get AC supply at our mains input. So before we get it converted into DC, we first change its voltage level from say higher level to lower or lower to higher as per our requirement in AC form itself. After that, we convert that AC into a DC using a circuit called rectifier, which we will be discussing today. But that rectifier output is sometimes having some AC component present within its output, as will be very clear when we discuss the rectifiers. Then we have to remove that AC component and this is done by using circuit that is called filter. Filter, as you know, the name is very clear. We are trying to filter out something. Here what we are filtering? We are filtering the unwanted AC or the frequencies of 50 Hertz or 100 Hertz or whatever are available. They should be removed. So that is the filtering process we subject our voltage to. So then we get a DC voltage. Now that voltage that we got from the filter is not a regulated. In order to get a constant voltage, irrespective of certain conditions like what is the load we are putting in or what is the fluctuation in the AC mains of our input, we should have a stable DC supply, and for that we use what is called the regulator circuit. So here diagrammatically I am showing step by step that we have a AC supply which is of 50 Hertz frequency, that we first step down. Let us consider that we are having certain requirement where we need a voltage which is lesser than 230 volts. So for example, let us take example of our battery charger or a cell phone charger, which is like typically requires 5 volt DC. Then we have to first step down that AC voltage, that 230 volts that we got, to a level which is comparable to 5 volts, something like say 10 volt or something. Reduce that voltage using step down circuit, then subject it to a rectifier. That rectifier will be essentially converting that AC into what is called pulsating DC. There will be a DC component in the output of a rectifier, but along with certain kind of pulses in form of a AC component present in it. That AC component will be filtered out by using circuit called filter, and then we subject the filtered output to a voltage regulator which gives a fixed DC voltage of our requirement, which we can connect to our load. So this is the block diagram of a typical power supply which you should engrave in your mind. And now the first component that we were discussing about is to convert the AC input voltage into desired value. This is done by a component called transformer. As you know, transformer is essentially having two coils. There is a primary coil where we are applying our AC mains supply, and there is a secondary coil where we are going to get our output of desired value. Now how does this happen? Basically by the induction rule. We are having AC current which is passing through the primary coil through a iron core around which these coils are wound. We can induce EMF in the secondary coil, and depending on how many turns of primary coil and how many turns of secondary coil are there, we get the output that is induced at the output of the transformer. When we give AC voltage to the primary coil, the changing magnetic flux is generated. Now that changing magnetic flux is essentially responsible for inducing EMF in the secondary coil via the core or the iron core, which is a common to primary and secondary. As per Faraday's law, the electromagnetic induction per unit turn in primary and in secondary remains the same. What does it mean? It means that entirely the voltage across the primary and the voltage induced across the secondary is solely dependent on the proportion of the turns of primary and secondary. Here if you see at the bottom, I have given the relation to you, that is the voltage in the primary upon voltage in the secondary is equal to the number of turns in the primary NP upon number of turns in the secondary. And of course the current relation is inverse here. The amount of current in the secondary to the amount of current in the primary is proportional to the number of turns in the primary upon number of turns in the secondary. The number of turns of primary to secondary is called the turns ratio, NPS to NS in our primary and secondary nomenclature. If we have number of primary turns more than number of secondary turn, implies that there is lesser amount of voltage induced in the secondary, because as per Faraday's law, the electromagnetic induction per unit turn is same. So if we have more number of primary turns and less number of secondary turns, means we have lesser voltage in the secondary and so it is called the step down transformer. We are stepping down the voltage from 230 volt AC to a certain lower value, which is equal to NS upon NP of V input. Now if we have primary turns lesser than secondary turns, then it is going to induce a higher voltage in the secondary than the mains input voltage, and that's why it is called a step up transformer. That is also quite commonly used, like if we have, say, some electron guns in our television circuit, the old kind of television circuits where we used to have cathode ray tube. There we used to operate these tubes at very high voltages of, say, some 1 kilovolt or 2 kilovolt. At that point of time, we had to convert the 230 volt AC into that kind of high voltage of kilovolt. So there we use the step up transformer. If we want to, say, design a typical transformer, then two things come into picture. One is the power input that we are going to give to the transformer, and what is the power output we are getting out of that transformer. The ratio of power output upon power input is called the efficiency of the transformer. And as you know, in any working system, the efficiency cannot be more than 100% ever. So you always are going to lose certain power in the operation of that particular device, and so always your power output is going to be lesser than power input. Typical transformers have efficiency of 80%. That is, the P out by P in ratio is of the order of 0.8. So keeping that in mind, if we want to have a transformer whose output voltage is 10 volt and the current that we are going to draw from that secondary of that transformer is, say, 10 ampere, then at output of that transformer, we are going to draw a power of I into V equal to 100 watts. Now, if we consider 80% efficiency, then we require to provide a power of 100 watt upon 0.8, that is 125 watts at the input of the transformer primary. With AC mains input of 230 volts, the required primary current will be P in upon V in, that is 125 watt upon 230 volts, which is approximately like 0.54 ampere or 540 milliampere. So as you see, as we are using in this particular case, the output current is very high, 10 ampere, but the input current that we require is merely 540 milliwatt or around half an ampere, 540 milliampere. Okay, so when voltage is higher, requirement of current is less at the input. Of course, the current rating as we are calculating here is going to basically decide on what gauge of wire we are going to use for the primary and secondary of the transformer. More the current, we need thicker coil or thicker wire used for winding the secondary. Whereas in primary, since the current requirement is lesser, we can use a thinner or higher gauge wire. The turns ratio that we are going to require is V in is to V out, that is 230 is to 10. So in primary, if we have 230 turns, in secondary we should have 10 turns, or in similar proportion you can always have, say, 460 is to 20, and so on and so forth. One important thing we should remember about the transformer is that the transformer voltage and current ratings are stated in the RMS or the root mean square values of the actual current and voltage. So if you want to talk about the peak amplitude of the voltage or current, for that matter, handled by the transformer, you have to always multiply the value of the voltage stated by root 2 so that you get the peak value. So just you remember that the voltage that we are stating for any transformer is actually just the 0.7 of its peak value that actually we are going to get at the output of the transformer as a sine wave. Okay, so that you, whenever you are going to choose the components, you should be careful about keeping into mind that the peak voltages and peak currents are going to be higher than the rating you are stating here, and take care of them when you are choosing the particular component for your device. Now if we turn to rectification, the output of the transformer is alternating, that is AC, with voltage varying symmetrically about 0 volt. To convert it into DC, it is necessary to shift this DC level of the signal away from 0 volt. So I am showing here in this figure, if you see, the input AC signal is symmetrically varying around the 0 volt here, that is the T axis that we have shown. So whatever is going positive is also coming negative. So effective DC voltage level is 0. But what we do in rectification is that we preferentially allow only a particular half cycle to flow through the rectifier circuit. At the output we get preferentially only a unipolar signal. We don't get any negative signal here. So effectively the DC content of this, the middle curve that we are seeing here, is higher than 0 volt. This is done in case of half wave rectifier. There is another type of rectifier, and we will be describing it in quite details, is full wave rectifier, where we are making use of both the half cycles of this sine wave that we are given at the input. That is the first, that is the positive half cycle is passed just like that, but the negative half cycle here, the one that is here, is inverted and passed through it. So what we are achieving here is that we are getting wave which is fully utilizing the input signal but converting the negative half cycle into positive and effectively increasing the DC level of this circuit. This is called the full wave rectifier. And now how to do it is we need certain electronic components which can actually do the operation that we just now looked at. And the best candidate to do this is a diode. You must have come across a diode. Is a simple semiconductor device which has got a P and N junction, and it has got a unipolar kind of behavior or a directional kind of behavior in its input output characteristics. Here we have just shown the rectifier diode symbol, where A is denoting anode and K is denoting cathode, just because A is the one that is going to be connected to positive and K is the one which is connected to negative in form of battery voltages when we apply them, or the supply voltages we apply them. Below here is actually the photograph of a typical diode, where this silver ring is representing the cathode. Or also here you are seeing very biggish kind of devices. These are the power diodes, which can handle very high currents or very high voltages. So there will be power dissipation will be high in this kind of things, and so we have good heat dissipation mechanism built within this. So these are different types of rectifier diode that we get. And here I am showing you the current voltage characteristics of a diode, where in left hand side figure here we have connected positive terminal of our supply to the P terminal or anode and the negative to the cathode or N terminal. Then this diode is going to initially slowly increasing current, but as soon as it reaches its knee voltage, as it is called, then it just shoots up. The current goes on increasing with very little change in the voltage across it. So this is going to be like, we can consider this circuit as if that this is a switch which is going to be put on, and it is going to give us a current flow through it when positive is connected to the P terminal and negative is connected to N terminal. But if we see the reverse bias condition, that is when positive is connected to the N terminal and negative is connected to P terminal, in that case, since the majority carriers are going to be drifting away from the junction area, we are not going to have any current or negligibly small current, which will be just due to the minority carriers in this particular device. So we get up for long time, that is a very high reverse bias voltage, we don't get a significant current. So as if this diode is not present, or as if there is a switch which is shut off, when the voltage of negative polarity is given to this particular device. And only after very high voltage what we encounter is a breakdown voltage. In this breakdown voltage, of course, we are going to destroy this diode because of overheating and all, and it is not normally recoverable. So we are going to have here, if we just bar this thing and if we work only within this range, then we can look at the diode as if it is a switch which conducts when it is in positive mode, but it is switched off when it is negatively biased or reverse biased. So this is exactly what is going to be helpful for our rectifier. We are going to have a rectifier where our AC input is varying around a 0 value. If we attach a diode like this, then whenever there is positive at the anode with respect to cathode, then that particular voltage will be passed through this diode. But in the negative half cycle, if you see what happens, negative half cycle, we have negative here, and through this and the circuit completion we have positive here. It is a reverse bias of the diode, and so this is a switch which is switched off. So diode as if is a open component here, it doesn't exist. So at the output we don't get any voltage, it's 0. Again, when in the second cycle, when it becomes positive at this end, then again the conduction of the diode starts. So we are able to remove the negative half cycle from the AC signal in this particular half rectifier. We are calling it half wave rectifier because only half of the wave we are using here, the remaining half is 0. So single diode is allowing us to only one half cycle of the sine wave at the output to appear, and while the other half cycle the output is 0. Now as you know, since we are successful now in removing the negative half cycle of the input signal, the DC component of that particular circuit output is going to be different than 0 volt. How much it is going to be? Let us just calculate with a small mathematics, not very complicated. Consider that we have a circuit of a half wave rectifier where R is the load that we are connecting, across which the output voltage V out, VO, is appearing, and VD is the knee voltage that I told you about, that is required by the diode for its own operation, but normally it is so small that we can even neglect it. Now consider that the input voltage V secondary, that is at the secondary we are getting a signal of Vm sin omega t, where Vm is the peak amplitude of the signal. Then what do we get at output? As you know that we are going to get the signal at the output only during the first half cycle, that is when the omega t, if we are going to have on the time axis, if we just depict it in the radians, then for omega t from 0 to pi we have Vm sin omega t appearing at the output as it is, but from pi to 2 pi we have got 0 volts. As you know, a sine wave is typically repeating after 0 to 2 pi. We have a full range of 0 to 2 pi, so it keeps on repeating after every 2 pi interval. So during 1 2 pi interval, the output at the VO is like Vm sin omega t for 0 to pi and 0 for pi to 2 pi. Now if we integrate this, then we get the DC component of this output voltage. So we integrate it as 1 upon 2 pi 0 to 2 pi VO d omega t, which is 0 to pi Vm sin omega t d omega t, plus from pi to 2 pi it is 0. So if I integrate it, I get sin omega t as minus cos omega t in the range from 0 to pi, and if I substitute the values of the integration limits, then I get here 1 upon 2 pi Vm into 2, so that is Vm by pi, or 0.318 of peak input voltage Vm. So 0.318 Vm is the DC component of the half wave rectifier. That is the same thing we are depicting here, that is on the left hand side. If you see this, follow this red line, the DC voltage is 0, but if you see here, the DC voltage level has shifted to 0.318 of the peak value Vm. There is another characteristic of a rectifier, and that is the diode rating, what kind of diode we should be choosing for our circuit. And very critical kind of parameter is the peak inverse voltage. As I told you that when the diode is given a particular negative voltage, after certain high voltage it undergoes breakdown, and it is unrecoverable breakdown, and the diode gets normally damaged after that. So we should have the rating of our diode in such a way that it will not break down even with a particular negative voltage across it, and that is called the peak inverse voltage. Now in our circuit, when the diode is not conducting, the entire input voltage at the secondary winding appears across the diode, and so the diode should be capable of resisting or withstanding that minus Vm voltage across it without any breakdown. This is the peak inverse rating of the diode required for our half wave rectifier. Now another component that we need to look at in our rectifiers is what is the root mean square voltage of our output voltage. The root mean square component of our output voltage, Vrms, is nothing but under root of 1 upon 2 pi integral 0 to 2 pi V output square. This is the standard formula of our root mean square. So if you just put the values, then we get from 0 to 2 pi Vm square sin square omega t d omega t, which will be divided into 0 to pi Vm square sin square omega t plus pi to 2 pi will be 0. So this component is 0, and Vm square is out of the integration sign. Sin square omega t d omega t we can always replace by 1 minus cos 2 omega t by 2 d omega t, and integrate it, we get omega t minus sin 2 omega t by 2 in the integration limits of 0 to pi. So if we substitute the values of 0 and pi in this sin omega t, it is going to be 0. So omega t is the only surviving component here, which will be giving us output of Vm square by 4 root, that is Vm by 2. So the RMS voltage of our half wave rectifier will be Vm by 2. Now when we are particularly looking at the instantaneous value of our output signal, this is the output signal I am showing of a half wave rectifier, then what is the instantaneous value? Say for example at this particular point, the instantaneous value of this particular point, VO instantaneous, is the DC component of the rectifier voltage plus there is some riding instantaneous AC component on it, which I am depicting by V prime. So this instantaneous AC component V prime is nothing but V output, that is the voltage at this point or instantaneously at any point of time, minus VDC. Now if I try to find the RMS value of this instantaneous AC component, it will be V prime RMS equal to 1 upon 2 pi integral 0 to 2 pi VO minus VDC square d omega t, that is 1 upon 2 pi 0 to 2 pi. I just expand this square term, V0 square plus VDC square minus 2 V0 VDC d omega t. Then we know that integral VO square 1 upon 2 pi 0 to 2 pi represents our RMS voltage square, whereas this component integral VO 0 to 2 pi d omega t represents the DC or VDC. So if I just substitute VDC in place of VO and VRMS in place of this VO square integral, then we get V prime RMS is equal to VRMS square minus VDC square under root. Why we have found out all these components is essentially to see how is the performance of our rectifier circuit is. And the important parameter that characterizes our rectifier circuit is the ripple factor indicated by gamma. It is nothing but the RMS value of the AC component of the output voltage upon DC component of the output voltage, that is V prime RMS upon VDC. So if we just substitute the value of V prime RMS is nothing but V RMS square minus VDC square, and VDC as just VDC in the denominator, and then if we just simplify it, then we get V square RMS upon VDC square minus 1 under root is the ripple factor. And if we now, since we have already calculated the VRMS value and VDC value, if we just substitute those two here for half wave rectifier, as you know, VRMS is Vm by 2 and VDC is Vm by pi, and if I just substitute them with square and then minus 1, then I get the ripple factor as under root of pi by 2 square minus 1, which if you calculate it is 1.21. There is another factor that is also characterized as the rectifier, and it is called the form factor. Form factor is simply the VRMS upon VDC. VRMS upon VDC is Vm by 2 upon Vm by pi, that is pi by 2 is equal to 1.57. And if you substitute this in the ripple factor, then gamma turns out to be under root of form factor square minus 1. If you put these values, actually you turn out to be the same ripple factor that I got it from the calculation of the RMS value of AC component. So if you don't want to do the RMS value of AC component, you can always go through the root of ripple factor in form of form factor to arrive at the same value. Now, how good is the rectification efficiency of our circuit? If RL is the load resistance and diode resistance is very small and that is negligible, the DC power delivered by our half wave rectifier will be PDC equal to VDC square upon RL, which is nothing but Vm by pi square by RL. And the input that we have given, the AC power delivered that we are giving it into the half wave rectifier is PAC, is nothing but V square RMS upon RL, that is Vm by 2 square upon RL. If I just substitute and then take a ratio, then the efficiency of rectification eta will be PDC upon PAC into 100% will be Vm by pi square upon Vm by 2 square into 100%. So if you just substitute the values, you get Vm square getting cancelled, 4 by pi square into 100%, that is 40.6%. So as you see, in half wave rectifier we are losing a lot of power and wasting it, and at the output we are just getting useful power of only 40.6% of what we had pumped into our circuit in the initial stage. So in order to better this, we use the scheme of full wave rectifier. Now here we are going to use, as you know, both the half cycles, and we need a circuitry which is going to even invert the negative half cycle into a positive half cycle. How to do it? For that we have two schemes essentially. One is called the center tap transformer type full wave rectifier, where we are having an AC source which is given to our transformer, step down transformer here, which is center tapped. Center tapped means the winding of this secondary is divided into two parts at exactly in the middle, symmetrically around the center these windings are done, so that this middle point is called the center tap, is symmetric vis-a-vis both the ends of the secondary coils. And to these two ends we attach two diodes in these directions, and then outputs of these two diodes we couple together and we attach our load, the load resistance across it, and the other end of the load is put to ground through the center tap. So this is how the circuit is completed. This is one way. Another way of doing the same thing is by using a combination of 4 diodes in a bridge form. As you are seeing here, we are having D1, D2, D3 and D4. These diodes are arranged in such a way that they are going to allow us to have this kind of output of full wave rectification, and we will now in couple of minutes see how these both circuits work. In the center tap transformer full wave rectifier, what happens in a positive half cycle? So in positive half cycle, the secondary, the upper part is positive, and whereas the lower part, this end is negative. So naturally the diode that is connected D2 is reverse biased because negative is on this side, but this diode, since there is positive on this side, is forward biased and it starts conducting, and through the load it returns the current. The current path is completed like this. Current is flowing from right to left in our load resistance. Now this is how we are getting our first half cycle, which is through the D1. If we go to our negative half cycle, in this case, this upper part of the secondary is negative, but the lower part is now positive. Since this lower part is now positive, D2 will be conducting, whereas D1 will be reverse biased. So current is going to flow through D2 and through load go back to the center tap. Now if you compare these two circuits, the direction of current in both the half cycles with respect to RL is same. In both the cases, the current is flowing from right to left. Okay, so at output, in the even negative half cycle, at load we see the output which is again flowing in the same direction. So this is how we are successful in reverting the polarity by using two diodes in full wave, and so by alternatingly positive and negative we are getting output which is now positive, positive, positive and positive, and this goes on like this. Now what will be the PIV or the peak inverse voltage in this particular case? See that due to conduction of D1, say if we consider a positive half cycle, then in that case our D1 is conducting, whereas D2 is the reverse bias diode. So we have to cater for what is the peak inverse voltage that this D2 diode should be able to withstand. So for this, since this is positive, D1 is conducting fully, consider that its internal resistance is 0, then that entire input is appearing across load. We get positive here and negative here of the input, and at certain point when peak voltage is there, this Vm is appearing across it. Now at the same time, in the lower half of our secondary, we have got negative voltage here and positive voltage here. Okay, so what is happening? We have Vm in this direction like this, positive here, and in series with that across the load again we have Vm. So these two Vms are adding up, which are coming parallel to our D2. So this reverse bias diode is going to encounter total of, if you consider from this point till this point, 2 Vm voltage across it. So the peak inverse voltage rating of a diode in full wave rectifier using center tap transformer should be 2 times Vm. Okay, so you need a higher diode rating. In half wave rectifier, as you remember, it was only Vm. Now if we go to the action of the bridge type full wave rectifier, here I have shown you on the left hand side here the positive half cycle what happens. In positive half cycle, here there is no center tap. This is a single secondary with single winding. Then positive is here. So this diode is going to conduct through D2, through RL, through D4, it is going to come back. So this is the direction of current in the positive half cycle. In negative half cycle, we are going to have a voltage where D2 and D4 are reverse bias, and this positive voltage from the lower part of the secondary is going to pass through D3, through RL, through D1 and back to the secondary. Now in both cases, the direction of current, if you see, is from right to left in RL. So same way as we had for our earlier center tap transformer, we do have here also both the half cycles treating to be positive vis-a-vis the load, and that's why we are getting once the conduction through D2, D4, another time we are getting conduction through D1, D3, but the resultant is same. PIV of this bridge type full wave rectifier is quite simple, because these two D1 and D3 are in parallel vis-a-vis RL, because D2 and D4, if they are conducting, then almost their resistance is 0, so they are almost short. So D and C points are together, A and B points are together. So whatever is voltage across the secondary, Vm, is going to appear across the load, and so also across D1 and D3 simultaneously. So both D1, D3 will have to sustain Vm as the peak inverse voltage across them. So the peak inverse voltage is now half than what it was for the full wave rectifier. The RMS voltage in this case, it will be calculated, since we are going to have a repeated waveform every pi, 0 to pi, then again pi to 2 pi also we are having the same kind of signal. So we do the integration from 0 to pi, and if we go on doing this simple mathematics, 1 upon pi integral 0 to pi VO square, and do the substitutions, then we arrive at Vrms is equal to Vm upon root 2. Same way, the DC voltage also you can calculate quite easily by integrating over only 0 to pi, and it comes out to be twice Vm by pi and 0.637, that is exactly double to that of the half wave rectifier. And the ripple factor, if you see here, is quite less, because V prime RMS upon VDC, which will be equal to V RMS square upon VDC square minus 1. If I substitute the values for the full wave rectifier, that is Vm upon root 2 square upon 2 Vm upon pi square minus 1, it comes out to be 0.482, and the form factor is 1.1. And the rectification efficiency also, if you see, by just substituting VDC square by RL for PDC and VRMS square upon RL for PAC, then PDC by PAC will be equal to 8 by pi square into 100, that is 81.2%, a very high efficiency. And that's why we are having very good performance when full wave rectifier is there. So in this table we are summarizing the performance of all these rectifiers. In order to obtain the DC voltage from the power supply, we need to remove the AC ripple present in that rectifier output. So that rectifier output has got certain frequency component. Like if it is coming from a half wave rectifier, it will be having a frequency component of 50 Hz. If you are having output from the full wave rectifier, then as you remember, from the full wave rectifier we have the repeated positive cycle and the negative half cycles of the sine wave getting converted into all positive half cycles. So effectively they are coming as the waves which are having double the input frequency. So if 50 Hz is our input frequency, then output frequency of our full wave rectifier output will be 100 Hz. So we have now frequency component which is to be removed. So the element which we will use to remove that should be having its impedance proportional to the frequency. So you remember that the elements called inductor or capacitor are having impedances which are proportional to the frequency of their operation. For inductor, the impedance is j omega L, and for capacitor minus j upon omega C. So whereas we have got these components, we can be sure that they are going to differently behave at different frequencies, and that is the thing that we are going to make use of to filter out the unwanted frequency component in our output of the rectifier circuit. Also now, if you remember that in rectified output, the signal would be going from 0 to V maximum and coming back, then again going up V maximum and coming back. So it is a kind of a sinusoidal signal only, which is variable from 0 to Vm, or the V peak amplitude of the input signal. Now when we want a DC voltage at output, we want the output of our circuit not to reach 0 value, but to remain at the average value of, say, typically near the DC component of the rectifier output is. This can be done by a certain scheme where we have component which is going to store the energy during the conducting cycle of the rectifier and use that energy stored within it to deliver it to the load when there is no input from the rectifier, right? So this kind of energy storage device is required in our application in the power supply applications. And again, inductor and capacitor are the easily available devices which come handy for use as a storage device. In capacitor, as you know, we store the charge, and that is stored as a energy which can be used in form of a current for our load functioning. In inductor also we can store the energy which can be used when the input signal is not available. The capacitance filter is the one where we are showing here the full wave rectifier output is given to a capacitor. This is the part which is of our interest now, which is connected then parallel to load. So what happens in our case is that this is a full wave rectifier output. Below here I am showing you. Then initially when I am having say conduction at Vm, then my capacitor charges to say value B. Now the output of my full wave rectifier starts going down in this cycle here. But since there is a capacitor which is charged, the load will be looking at the voltage which will be supplied by the capacitor. And so capacitor is able to give the energy to the load when there is no input available from the rectifier output. So the capacitor gets discharged to say value C. But again when the next half cycle of the full wave rectifier is coming, it gets charged also. So again it regains the value up till D, and again in the next portion it delivers that energy in form of energy to the load, and this effectively we are going to have voltage that is looked upon by the load is not like varying from 0 to Vm, but varying around VDC, and which is remaining like charging and discharging around this value of effectively VDC. So when input from the rectifier is falling, the energy stored in the capacitor is given to the load, and instead of reaching 0 volt, the voltage now just reaches up to point C and again rises up to point D. So we are now able to convert this pulsating DC into much smoother DC. Now of course the performance of this filter is going to depend on the value of load also. If my load resistance reduces, means there is larger current flowing through it. So when requirement of larger current is there, this capacitor is going to get discharged faster. So in such cases, the voltage that instead of reaching till point C here, it will reach little below here and then go up. So performance of a capacitance filter will be highly dependent on what kind of load current is required by our circuit, and so the performance will be hampered if large currents are drawn. So we have to take into cognizance while designing or choosing the capacitor in such a way that it will be having a value enough to store energy which will be able to deliver enough current to our load when conduction is not happening. But it should not be so high also that it takes longer time to charge, because if you remember, the charging and discharging of capacitor is happening in exponential relationship, and that is dependent on the RC value of the circuit components. So that RC is called the time constant of the resistance capacitor circuit, and that RC time constant is the main determining factor in optimum design of our rectifier. We can also use inductance as or the choke as a filter, where the property of the inductor to oppose the change in the current is used for our filtering action. In this case, when the output current of the rectifier is increased, the energy stored in the inductor in the form of magnetic field, that output current from the rectifier is used for storing the energy in our inductor, and then it gives out that current when the current at the load falls below the average value. So effectively this is also going to be operated in the similar principle, that the energy stored in the device is given to the load when there is no conduction happening from the output of the rectifier. But remember that this L filter works only when the full wave rectifier is there. If you have got half wave rectifier, that is when there is a full conduction in the half cycle and then there is complete zero at this one, since inductor filter opposes any change in the current, its functioning is very poor when half wave rectifier is used. So inductive filters are preferentially used only when we are having the full wave rectification. And in this case, since this inductor is always of the property to oppose any change in the current that is flowing through it, then the output that reaches in the load resistance is not as high as was happening in case of the capacitance filter, because the capacitance was charging there till the Vm value. So always you are getting the voltage at the output which was equal to Vm when the capacitor was fully charged, and then it was slowly coming down. But in case of inductor, at no point of time will it allow that entire Vm to pass through to your RL, and so the maximum load voltage will always be less than Vm. But we can always have combination of LC filters, where we can have one type is the capacitance input filter, or a PHE filter as we call it, where we have got capacitance in shunt with the load as well as in the output of the rectifier circuit, and there is in series L circuit. Now in this circuit the ripple is quite less, but the voltage regulation is little poor, because this capacitor C1 is the one that is keeping on charging and discharging as per the input cycle from the rectifier, and so this capacitor is going to discharge at certain point of time in order to supply to the load, and so this voltage itself at this point is not going to be constant throughout the operation, and so the voltage regulation will be quite poor in this scheme. But we can also have something called an L filter. L is in the shape of the component arrangement here. There you are at the input we have an inductor, and a capacitor is put in shunt or in parallel with the load. In this case the voltage output is smaller than the capacitor input filter, as I was telling you, because capacitor can charge to the maximum value, whereas inductor will never allow this capacitor to charge to maximum value. But if there is any change in the load current, then effect of that change will be very less on the output voltage. So output voltage will be quite stable irrespective of change in the load conditions, because in case of capacitance filter, if you remember, the load change was affecting because change in the discharging time of the capacitor. But here in this case this is not going to be the case, and so we are going to have lesser effect of the change in the load on the output voltage. I thank you very much.